Logarithmic and exponential equations. All right, all the work we've done to date is going to be pulled in to this video lecture. We've talked about logarithmic functions, exponential functions, the fact they're inverses, properties of exponents, properties of logs. It all comes into play here with our objective: solve logarithmic and exponential equations algebraically and graphically. Let's remind ourselves what we know that's going to be important here. We know the following. We know that exponential functions and log functions are inverses. We use one of those to undo the other, and that's going to take place, that's right down here, which I'll talk about in just a moment. We know what the log function is. It's a function of the form f of x equals log base a of x, where x and a are positive and x is not equal to 1. We know the domain of the log function is the positive numbers, the set of all x's such that x is greater than 0. And we know that the exponential function and the log function are related as follows. Okay, an exponential function, a to the x is equal to y. As a reminder, an exponential function has the variable in the exponent. Okay, that can be rewritten as a log function, log base a of y, y being the argument, is equal to the exponent. Again, that's the log function. The output of the log function is an exponent. Okay? Let's remind ourselves the properties of logarithms. I'm not going to go over or read through these again, but I will say that alongside this is a very important thing we're going to make use of today. The other one we're going to make use of a lot today is property number 6 down here as I've written it. And that says that if we have a positive number equal to a positive number, a positive something equal to something, a positive something equal to a positive something, then the log base a of the left side is equal to the log base a of the right side. Now, it's this direction, it's the direction from right to left that's going to come into play in this video lecture. If I have a log base a of something equals a log base a of something else, then I know that the something equals the something else. So these two pieces, this piece here and this piece here, are going to be key to solving logarithmic and exponential equations. Again, this piece up here and this piece down here. All right, how do we do it? Well, let's talk about the steps for solving logarithmic equations algebraically. As necessary, rewrite the equation using the properties of logarithms so that it is written in one of the following ways. First possibility, the log base a of x equals c. If you can write it in this way, you can change it to its exponential form and solve it. The second possibility, 1 of the logs base a of something equals 1 of the logs base a of something else. Okay, you can't have a number in front here. A log base a of something equals a log base a of something else. If you have that, you can drop the logs. Which is what we see in step 2 here. If you get this figured out, if you can rewrite it in this form, change it to its exponential form and solve it. If you can write it in this form, then you can use property 6, which says you can drop the logs and have something equal to something else. A unique piece with log functions is you want to check the solutions. Remember, the domain of the log function is positives. Okay, only positive numbers can go into the log function. So the argument must be greater than 0. So you must check the argument, or you must check the arguments once you find your answer or your answers. Let's get started. I've got 4 examples of log equations to look at. All right, first one. Log base 3 of 4 is equal to 2 log base 3 of x. Now don't get confused here. You can't just drop the logs. This is a log of something equals 2 log of something else. You can't drop the logs unless you have 1 log of something equals 1 log of something else. So let's use our log property and let's move that 2 from the front to the exponent, which we can do. So now I have log base 3 of 4 on the left is equal to log base 3 of x squared on the right. Now I can come up here and I can use this. 1 log base a of something equals 1 log base a of something else. We can drop them. Okay, so come down to here. I can now say, hey, cool. 4 equals x squared. And that's easy to solve. Square root both sides. X is equal to positive or negative 2. Okay, what have I been saying? Check the arguments. Okay, let's check those. Let's put in positive 2. This side's just a line. That's just a number. Let's put positive 2 into here. That's a positive argument. Positive 2 is good. Let's put the other answer possibility is negative 2. Negative 2 is not in the domain. Okay, so x cannot equal negative 2. So x only equals positive 2. Okay, again, your argument of the log function must be positive. If negative 2 is the argument, it will not go into the log function. You will not get an answer. So your only possibility of these two, negative 2 is extraneous, positive 2 is the solution. Let's check this with our calculator. Alrighty, let's take log base 3 of 4. Let's see here, log base 3 of 4 is on the left side. I'll press enter, I'll get a decimal approximation right here. And let's take 2 log base 3 of 2, because we think x is equal to 2. Let's put 2 in there. And I get the same number. So I just checked using my calculator that 2 works. If I were to put negative 2 in there and I were to check negative 2, 2 log base 3 of negative 2, remember that was a solution that came out. It's going to say nope. Non-real, not happening. Okay, non-real answer. We're dealing with real answers, not going to happen. So, okay, let's solve this graphically. All right, to solve this graphically, we'll just set y1 equal to the left side, so log base 3 of 4, and that's simply a number. That's an exponent, so that's going to be a horizontal line somewhere. And we'll set y2 equal to the right side, 2 log base 3 of x. And let's see what happens. Where they intersect is going to be our solution. So y equals, we're going to do log base 3 of 4. And again, if I put that in my graph, whoops, that's just a horizontal line. Y equals, it's an exponent, whatever that number is. Okay, let's go into y equals, and let's put in 2 log base 3 of x in for y2. I'm down here. I'm going to do my zoom to standard, and there's my y1, which is just a horizontal line. Here comes y2. And they intersect right at this point here. We can do a second calc. And number 5 is the intersection. Pick first curve, pick second, pick second curve. Okay, there we go. Take a guess. And sure enough, out comes x equals 2 here, which is the solution graphically, and we got the same solution as we have here algebraically. All right, let's move on to some a little more complex. We'll get a little more complicated as we go along here. Example 2, log base 2 of x plus 2 plus log base 2 of 1 minus x is equal to 1. I'll give you a hint. Whenever you have a random number floating around someplace, it's very difficult to get it to be log equals log. So what you want to get is 1 log on one side of the equation. Well, here we have on the left side the sum of logs. And we know from our log properties, the sum of logs is equal to the log of the product. So this is equal to log base 2, and I'm going to use brackets, x plus 2 times 1 minus x equals 1 on the right side. Again, the sum of the logs is equal to the log of the product. Let's do some math with that argument. This is x minus x squared plus 2 minus 2x. And I can clean this up. This is log base 2. I'll write the x squared term first. I'll write the x term second, and then the constant third, and I'll be here. Okay, I've got the 1 log on the left side and a constant on the right side, so I can rewrite this in its exponential form. Base to the exponent equals argument, so negative x squared plus x plus 2 equals 2. Oops, I should have written that the other direction. Sorry about that. Doesn't matter, but I wanted to be consistent. 2 to the first power equals negative x squared plus x plus 2. Well, it's a quadratic. Let's set it equal to 0. X squared. I made a mistake someplace. This is a minus x. I bet you caught that. All right, that's a minus x. Sorry about that. This is a minus x. I'm looking at my notes and realizing I made a mistake. Let's see. Negative x squared minus x plus 2. Okay, 2 to the first equals, that's correct. Set it equal to 0. X squared plus x, equals 0. It's a quadratic, but it's quickly factorable. Factor out the x. I have x plus 1 equals 0. So x is equal to 0, or x is equal to negative 1. Okay, what do I say? Check arguments. Okay, let's check 0. If 0 goes in here, well, 0 plus 2 is 2. That's positive. If 0 goes into here, 1 minus 0 is 1. That's positive. So x equals 0 is good. Check negative 1. Check the arguments. Negative 1 plus 2 is positive 1. That's good. 1 minus negative 1 is 2. So we have 2 answers. X equals 0 and x equals negative 1. With your calculator, checking this algebraically, put 0 into here, put 0 into here, put this into your calculator. You should have 1 come out. Put negative 1 in here and here. Run this through your calculator, and 1 should come out. Let's solve it graphically. Okay, again, graphically, we're going to have y1 equal the left side and y2 equal the right side. So y1 equals a long expression, log base 2 of x plus 2 plus log base 2 of 1 minus x. That's quite something. y2 equals 1. That's a horizontal line through y equals 1. That's not bad at all. And we're hoping to get the answers of 0 and -1 is where they intersect. We should have 2 intersection points. Okay, so I'm going to be here. I'm going to clear out my previous. Okay, so I have log base 2 of x plus 2 plus log base 2 of 1 minus x. Okay, that's y1. y2, as I mentioned, is just simply a horizontal line through y equals 1. Let's press graph. Well, there's the first one, that kind of long expression, and here comes the line. Well, it looks like they intersect right in this area. Let's zoom in, like going from -2 to 2. Let's zoom in. Go to our window. Let's go from -2 to 2 and from -2 to 2 on both the x-axis and the y-axis. Here comes the first one, y1, log base 2 of x plus 2 plus log base 2 of 1 minus x. Looks like there are some vertical asymptotes, and here comes the horizontal line. Sure enough, I have 2 points of intersection. Second calc. Intersect. I'll go to the left one first, which I think is -1. Sure looks like it. I got it. It intersects at -1. Well, that we had here was one of our answers. And let's go back to this other point. So second calc, they intersect. Let's go closer to over here. And again, that sure looks like x equals 0. And 8.846 times 10 to the -14th. Yep, that's about as close to 0 as you can get. The calculator, of course, maybe has some pixels or some accuracy issues based upon resolution, but this is 0.130088. I think 0.130088 is close enough to 0 for us. All right, so let's look at a couple more examples. This one uses the natural log, which we know is the log with a base of e. Okay, so I have the natural log of x minus 1 on the plus the natural log of x on the left. And I have the natural log of x plus 2 on the right. Well, if I could get these two logs together, then I would have natural log equals natural log, and then I could drop the logs. Well, this is a sum of logs, and that's the same as the log of the product. Well, before I drop the natural log, let's clean up the left side. This is the natural log of x squared minus x equals the natural log of x plus 2. There we go. Log base e of this, of something, equals log base e of something else. So that means that the something equals the something else. Great. Quadratic. Set it equal to 0. X squared. Let's subtract x's. So I have minus 2x. And I have minus 2 equals 0. I'm going to look at that. That is not factorable. So I'm going to use my quadratic formula. X is equal to opposite b plus or minus square root b squared minus 4 times a times c, all of that over 2 times a. Okay, what is this? This is equal to 2 plus or minus, I think this is the square root of 12 all over 2. Well, 12 is 4 times 3, so this is 2 plus or minus 2 root 3 over 2. So this is 1 plus or minus the square root of 3. All right, 1 plus or minus the square root of 3. Well, let's see here. 1 plus the square root of 3 is approximately equal to what? Because I want to check my arguments. So let's go into here. Let's quit out of my graph. 1 plus second square root 3. That's approximately 2.73. And 1 minus the square root of 3 is approximately 1 minus the square root of 3, negative 0.73. All right, we want to check my arguments. Okay, so I'm going to do here, check arguments. Let's check 2.73. 2.73 minus 1 is positive. 2.73 is positive, and 2.73 plus 2 is positive. 2.73 is a possibility as a solution. Let's check negative 0.73. Well, negative 0.73 minus 1 is negative. It's already out. If we go to here, it's only negative 0.73. It's out twice. It's positive here, but it's negative for these two arguments. This one is out. So my solution is only one solution. X is equal to 1 plus the square root of 3. We could put all that in here and check it with the calculator. If you want to graph, let's graph both sides. Graphically, we think the intersection should be at approximately 2.73 because that's the answer. Let's do this graphically. Let's solve this graphically. Let's clear these out. So the natural log of x minus 1 plus the natural log of x, that's equal to y1 on the left side there. y2 is on the right side. It's the natural log of x plus 2. Okay, let's graph those. Oh, I forgot, I zoomed in. And it looks like I'm not going to quite make it with my zoom in. Okay, I think I've got is that a plus there? Yeah, that's a plus. Okay, kind of a small. Let's zoom out. Let's zoom to standard. Here comes y1, maybe. My calculator is on the fritz a little bit here. Let's go to second off. Turn it back on. And let's try again. There's the y1. Here comes y2. They certainly intersect right there. I'm hoping it's right around 2.73. Second, calculate a point of intersection. Okay, let's find my first curve. There it is. First curve, second curve, take a guess. Sure enough, 2.73, 20508. So I feel pretty good about my approximation right down here. All right, let's look at one more example, and then we'll do a couple of examples of solving exponential equations. Here's one. Natural log of 3m minus 1 equals 2 plus the natural log of m minus 3. Again, here's a number floating around. Whenever you have a number floating around, you're really not going to have, you're going to struggle if you're going to be able to get log equals log. Your better bet is to get logs on one side and have a log equals a number. So let's subtract natural log of m minus 3 from both sides. So natural log of 3m minus 1 minus natural log of m minus 3 equals 2. Okay, the difference of logs is equal to the log of the quotient. So this is the natural log of 3m minus 1 over m minus 3 is equal to 2. So now I'm in a good place. I can now change this to its exponential equivalency. There's an e here. E to the exponent equals the argument. So e squared equals 3m minus 1 over m minus 3. Now I need to do some math. I'm going to leave, I know e squared is a number, but if I do it, I'll have an approximation, and I want the exact answer, so I'm going to leave e squared alone. I'm going to multiply both sides by m minus 3 to get rid of the fraction. So e squared times m minus 3. I remember I need to solve for m, 3m minus 1. I'm going to distribute the e squared. E squared times m minus 3 times e squared equals 3m minus 1. Let's get variables on one side, constants on the other. So e squared times m minus 3m is equal to -1 plus, let's see here, plus 3e squared. Okay, I'm making a mistake someplace. Let's see here. My work is telling me I might have a mistake here. Maybe not. Let's check myself. M minus 3, 3m, e squared equals 3m minus 1. Okay, that's correct. 3m minus 1, subtract 3m, add. Okay, so now I can factor the m out. E squared minus 3 on the left equals -1 plus 3e squared on the right. And I can divide both sides by e squared minus 3, and I have -1 plus 3e squared over e squared minus 3. Okay, so there's the answer, I think. I'm going to leave this one. You can check by putting this into your calculator and getting an approximation. And then you can put that into here, and these two sides should be equal. Get the approximation here. And, I should check my argument no matter what. And then you could then check it with your graphing calculator. Let's make sure the argument. This is approximately equal to, let's see here. Let me move this over a little bit. That's a mess, isn't it? Okay, let's get out of my graph. So I like my fraction bar. -1 plus 3e squared over e squared minus 3. Well, I got 4.8227 approximately. And just by checking my arguments, let's look up here. Well, 3 times 4 minus 1, that's of course positive. And 4.8 minus 3 is positive. So I feel pretty good, at least that it does match up with the argument and need to be positive. And so I feel good about this answer. Again, you can put this into here and here, or you can graph y1 equals this and y2 equals the right side, and see if they intersect at approximately 4.8227. I'm going to move on to exponential equations. Okay, so here we are. How do we solve these exponential equations? Well, step 1, as necessary, rewrite the equation using laws of exponents so that the exponential part is isolated. Okay, if possible. All right, write the resulting exponential equation as the equivalent log equation and solve. Okay, so let's take a look here. 3 to the x equals 7. Step 1 is done. Okay, so we know this is right as the equivalent log. This is the log. If 3 is the base, 3 is the base. If x is the exponent, x is the exponent. A log gives you an exponent. And then the 7 is the argument. And there's your answer. X equals log base 3 of 7. So x is equal to approximately, let's put that into our calculator. Let's see here. Log base 3 of 7. 1.7712. 1.7712. Now, you can also, we can also say, remember, when you have something equals something else, you can take the log of both sides. So let's do it another way. So I have 3x is equal to 7. I can take the log of the left and the log of the right. Exponent moves in front. So I have x, So I have x times the log of 3 is equal to the log of 7. And I can solve for x. by dividing both sides by the log of 3. The log of 7 divided by the log of 3. Okay, now if you look closely, this is written with the change of base formula. We can check it. We better get approximately 1.7712. Okay, log of 7 over the log of 3. Same thing. See, that matches right above there. Or we can do the same thing with the natural log of both sides. You can use any of the same base you want. So the natural log of 3 to the x is equal to the natural log of 7. Okay, again, the x can go in front. X times the natural log of 3 equals the natural log of 7. Divide both sides by the natural log of 3. And x is equal to the natural log of 7 divided by the natural log of 3. If you do this division, you'll get this answer again. Or graphically, though you won't get the exact answer, you'll get an approximation. Again, y1 equals the right side, y2 equals the left side. So y1 equals 3 to the x, y2 equals 7, which is a horizontal line at y equals 7. Let's go into here. y1 is 3 to the x, y2 is 7. I'm going to go standard. Here comes 3 to the x. Here comes y equals 7, red line. And I'm hoping they intersect right around 1.7712, which is what we got. Second calc, intersect. I'll go up pretty close, why not? Enter first curve, second curve, take a guess. 1.7712437. So there you have it. I just solved this one in 4 different ways. Now, a little different here with example 6. Notice we have an exponent on the left side and one on the right side. I don't have a base I can work with to make them the same. So we're going to use this same rule we just did right up here. We're going to take the logs of both sides. Now, for the heck of it, I'll take the natural log. It doesn't matter. Excuse me. I'll take the natural log of both sides. A little easier on my calculator. Okay, now that allows me to move the exponents in front. So this becomes x times the natural log of 9/4 equals 1 minus x. Keep the exponent with parentheses because there's more here than just a single number or letter, times the natural log of 9. Remember, I'm trying to solve for x. Let's distribute. X times the natural log of 9/4. Remember, the natural log of 9/4 is just a number. This is its exact form. And let's distribute. This is the natural log of 9, 1 times the natural log of 9, minus x times the natural log of 9. All right, let's get my x's together. So on the left side, I have x times the natural log of 9/4, and I'm going to add x, l, and 9 to both sides. X natural log of 9 equals the natural log of 9. Now I can factor the x out. X times the natural log of 9/4 plus the natural log of 9 is equal to the natural log of 9. I have 1x multiplied by this, so I'll divide both sides by this expression. X is equal to the natural log of 9 divided by the natural log of 9/4 plus the natural log of 9. Nothing you can do with that. Remember, There's no such thing as a common numerator, so you can't start simplifying anything here. That's your answer, and that's the exact solution. If you put this into your calculator, you're going to get an approximation. If you put this in your calculator, you go out maybe 4 or 5 decimals, you can put that here and here and see if those two things are true, or you can check this approximation by graphing y1 equals this, y2 equals that. So that's a lot. We just finished up a lot of work on solving logarithmic equations and exponential equations.